identification of the maximum energy requirement was allowing us to define what is the pinch point, and the pinch point was dividing the system into subsystems. Above the pinch point, the process is globally asking for heat, which means that the hot streams needs to be cooled down by doing heat recovery. And below the pinch point, the system has an excess of heat, which means that the cold streams, the streams that needs to be heated, have to be heated by doing heat recovery from hot streams. And I know that I have enough heat in the hot streams to realize it. From there, we were able to identify where were the penalizing heat exchangers, so the heat exchangers that should be modified, so that are creating a penalty, and the penalty being the difference between the maximum heat recovery and therefore the minimum heat needed and the present energy bill. And from there, we have also been able to define a method that was able to allow us to create the heat exchanger network that does the heat recovery that is targeted by matching the hot streams with the cold streams, with a list of feasibility rules that were allowing us to finally define what is the design, so the structure of the heat exchanger network, with the appropriate splitting of the streams and the appropriate matching in such a way that we were realizing the heat recovery with the minimum number of units, and we were able to calculate those the minimum number of units, and even estimate how much it would cost to buy the heat exchanger network before being able to design the heat exchanger network, which was also allowing us to say, okay, we know if it makes sense or not to invest in the heat exchanger network. So today, what we are going to do is to look at another important question. So, how do we define the hot and the cold streams in a process? Because if I'm not defining the hot and cold streams in the right way, I will not define the right pinch point, and therefore will take wrong decisions everywhere. So it's important to say, okay, as we have a tool that allows us to identify what is the maximum heat recovery potential, then we have to ask ourselves, do we have a method that allows us to be sure that the hot and cold streams are well defined? And this will be the subject of the course today. So for doing this, we have to look at the process, and the process is defined by a process flow sheet that can be quite complex. So I hope that you cannot read this flow sheet because it is much too small. But this is typically what you receive. The reality is that you receive more than one big sheet where you have the processes that are described. And for this process, what we have to do is first to draw system boundaries, because we need to know what is the purpose of the process. The purpose is to produce products out of the raw materials. And for doing this, the system is going to use energy resources that will be converted and that will be then afterwards distributed to the process unit so that they can deliver the purpose. As the system is not 100% efficient, the part of the energy that will not end up into the products or the energy services will end up as waste that will be released in the environment, and that will create the emissions of the system. The emissions can be in the solid, in the liquid, or the gas phase form, and in addition can be in form of heat losses that will be released. Which means that at the end we can always plot an economic balance by giving a value to all the flows that I have, so the raw material bill, the energy bill, and the waste management bill. Typically the heat losses do not cost anything, so but otherwise if you release a pollutant, typically you have to pay for it. If you release wastewater, you have also to pay for it. And therefore we have the three costs that are identified here, and that have to be compensated with the sales of the useful products and byproducts that the system is going to produce. And I'm going to, in order to illustrate my talk, I'm going to use a an example of a process that is producing beer from from raw materials. Typically, from the energy point of view, the only thing that I see is the gas bill. So typically, I'm able to say, okay, I have a gas boiler that is consuming a certain amount of gas. Perhaps that I will know also how much steam is produced, how much cooling water I'm using, how much electricity I'm using for the refrigeration cycle. But typically, I do not see much more than this. Okay, when I'm the energy system engineer. On the other hand, you have the process engineer that knows perfectly how much beer he's going to produce, with which recipe, and how much raw material they will need, and they will hope and they will ignore most of the time the energy bill. Okay, and this is first difficulty. So what I see from the energy point of view is therefore mainly energy bills. So now we have to ask ourselves, so what does it mean? And how can you use this information in order to define the hot and the cold streams that I need if I want to identify heat recovery? So for doing this, we have to understand the reason why we are using energy in the process. So what is the role and the purpose of using energy in the process? Sometimes it's because I have to compress flows, sometimes it's because I have to heat flows, sometimes it's because I have to cool down flows, sometimes it's because I have to crush things. So I need to understand the reason why I need the energy. And for this, I have to divide the process into what we name the process unit operation. There is a list of process unit operations that are needed to convert the raw materials into the product or the byproducts that I will need. And this will be the first step. So I identify what are the real purpose of using energy in the process. And when I'm doing this, I will characterize it not only in terms of heat, but also in terms of quality of the energy, meaning I will always try to keep in mind the exergy value of the different flows. I will also ask myself if the system boundaries are the right boundaries. This is mainly when I'm going to look at the waste management. I can always release a waste stream in the environment, provided that it is in the right conditions. But perhaps it would make sense to think about treating the waste myself, so not asking someone else to burn my waste, but doing it on site, because then I can recover the heat. But I could also ask myself if I could not have additional products or revenue out of my system. So for example, by producing a byproduct that can be sold to someone else as a raw material. Let's assume that I am able to capture the carbon dioxide from the brewing process. I have carbon dioxide that is emitted. So perhaps that I would be able to take this carbon dioxide and use it to produce sparkling water. Or make a deal with Soda Club, right? And this would then add a new value to my process. Another dimension that I need also to look at is under which form do I buy the raw materials? So I can buy wood in logs, or I can buy logs in trees, right? And I can take the whole processing steps on my side instead of asking someone else to do it and have to pay for it. Okay, so this means that perhaps there are also opportunities there in the preparation or in the conditioning. Okay, for example, I'm going to produce beer, but the important is not the beer that I'm going to produce, is the beer that I'm going to distribute in a bottle. So I have to consider that the bottle is part of my process as well. Okay, so, and what is the method for doing this? And I would say that you have to learn to impose a first rule. And the first rule is that there is no taboo. Okay? So let's try to provoke the process. Ask the process what is the energy that it really needs. Not the way it is using the energy today. I can always burn natural gas to heat water at 30 degrees C, but it's not a good idea. Okay? So we have to ask ourselves what is really the needs of the heat. And I'm going to use to show you some examples. And when I'm saying no taboo, it doesn't mean that you are not going to accept constraints. But the idea is that we will start without constraints. And then if someone is going to say, okay, but this stream that needs to reach 30 degrees C, I need to do it with natural gas, then we will say, okay, it's not a problem, but I can show you the difference between the solution without these constraints and the solution with the constraint. And there will be a cost difference between the two. And then you will say, okay, if you accept to pay so much to use this, to impose these constraints, then no problem, we accept it. Okay? But typically, the people are not aware of the constraints that they impose. And most of the time, the constraints are comfort constraints. It's much easier to heat something by burning gas or using electricity. Okay? So it's more comfortable. But it doesn't mean that it is efficient. Okay? From the system point of view. So the no constraints principle, the no taboo principle is very important, which will allow you to give a value to the constraints, and that's something which is important, and also to identify which are, among all the constraints that you have heard about, which are the ones that are really constraining and that are really creating a penalty. The other one, okay, use it, it's not a problem. Okay? So that's a principle that is very important. So now we are going to concentrate on the process units. So what is happening inside the system? And we are going to quantify the amount of energy that is needed for each of those units. To measure the consumption, we will have first to differentiate the different types of or different forms of energy usage, and then to try to identify the measure of the energy usage, which will most of the time be related to the amount of energy per unit of product delivered at the gate of the plant. Okay? Which allows us then to have a performance indicator, because then we will know how much steam we use per unit of product, how much gas we use per unit of product, how much electricity we use per unit of product. And this is a very nice indicator, because if now your boss says, okay, I want to produce more, you will know how much steam you will need more, how much electricity you will need more, how much gas you will need more. Okay, so the specific consumption will be a very good indicator, and it will allow us as well to compare ourselves with our neighbors. Okay, it's possible that your competitors have a plant that is twice the size of yours. Okay, but they have perhaps a better efficiency than you. And by working with specific consumptions, you will be able to see if you are or not better than your neighbors. So the specific consumptions will be important. When I have the specific consumption, I'm able to calculate the annual energy bill, because I'm multiplying the production that I have done by the specific consumption to have and the cost of energy to have the final energy bill. So the specific consumption is important, and which means that inside the process you will have also associated flows to the process. So for example, how much cleaning water do I need per unit of milk that is produced? Okay? And afterwards you will have how much energy do you need to produce 1 unit of cleaning water that is used per unit of product. Okay? And this will also then allow you to have a better understanding of the sensitivities inside the process. Another dimension that is important is the fact that sometimes the processes are not operated in a continuous way. An example is the beer production. So if you produce beer in your house, what you will do is that first you will heat the pots with the mixture. Then you will evaporate, and this will make an hydrolysis. And then you will cool the content and you will put it into a refrigerator. Okay, and then you will leave the tank, wait for a certain time to let the fermentation process happen. Okay, so each one of those steps are needed and require heating or cooling. Okay, per unit of product. But will not define a clearly power, because you will have a certain power when you heat and another power, so a rate of energy, when you have to cool. And typically what we will nevertheless do in order to do the heat recovery is that we will try to neglect or to hide the variations. And this is especially because I'm going to make something which is industrialized, meaning that even if I have one tank that is under fermentation and another one that is in boiling, typically I will try to organize the production in such a way that my boiler will operate the whole year. Okay? Which means that I will have several tanks that will be heated one after the other, and I will do a system, a scheduling that allows me to work one after the other. Therefore, when you will define the hot and cold streams, a trick that can be used is what we name time average, which is finally defining the consumption as a function of the kilograms, so the specific consumption that you will multiply by the specific production, or by the production, and divide by the operating time to have a mean power. Okay, this is a time averaging method that will allow you to know what is the typical amount of energy that is needed at a given time in a mean value. And the mean value, of course, is something which will have to be taken into account when you will buy the heat exchangers. Because now, if this mean value has to be supplied in 10 minutes or in 1 hour, of course, the size of the heat exchanger will be different. Okay? So the time average is one trick. I say, now, how do we analyze the process units that are happening there? So the first thing we have to do is to make the flow sheet, so the interconnections of the different process units in such a way that I have a flow that is going from the inlet to the outlet. And then we are going to look at the different process unit operations that can do separation or physical operations. It can be filtering, distillation, membrane, that can do chemical reactions, or they can do still just melting and separation, for example. Something which is important at this stage is also to realize that one unit operation can be done in different ways. So, for example, for separating one fluid from another, I can use a membrane, I can use a distillation, I can use an extraction. And I have to keep in mind that the goal is to do the unit operation. It is not necessary to do it in the way it is done today, right? And then we have to understand in each of those unit operations, what is the role of energy? So why do I need energy? Do I heat just to increase the viscosity, or do I heat because it creates a chemical reaction? Okay, so it means that I have to understand the reason why I need to reach the temperatures that are needed. And the same for the use of compressors in the system. So sometimes you produce compressed air just to create, to to create an inert environment above a given tank, which means that in fact you do not need a compressed air at 7 bar, but at 1 bar is enough. Okay, so you have to realize or to really define what is really needed, right? By analyzing the process unit operations. The same when we are using electricity, because electricity can always be converted into heat or work, right? And sometimes the heating effect is part of the mechanical effect. But it means also that if there is a part of the electricity that is used only for heating and another part that is used just for making the things move, it would be better to heat with another way and then move the fluid, for example. Okay, so that's something that you have to analyze when you look at the process. Which means that at a certain time we will have a flow sheet like this, where we will identify what are the functions in each of the unit operation, and then define what is the role of the energy sources there. Let's take the example of the beer production. So if you have to produce beer, in fact what you do is that you take malt and water and you start to make a mixing here that is needing already some heat. Then afterwards you add water here and then you do a filtration. And then afterwards you go into, from the filtration you obtain some husk, and the wort that is coming out of this first operation is going to the cooking. In the cooking you do an evaporation and you break the molecules, so you make the sugar accessible to the fermentation. Once you have finished the cooking, then you go to the cooling. Then you cool down, then you add the yeast, and then you do fermentation. After a certain time, you have produced the ethanol, and then you have to stop the reaction. And to stop the reaction, you cool it down to a lower temperature. And here, as you are smart, you are going to add water in order to regulate the amount of alcohol that is in the beer that you are going to supply. Once you have done this, then you have to go into the packaging, and for the packaging you realize that you need to clean sometimes and to pasteurize the mixture of the bottle or the can and the beer in order to supply the beer on the market. And for doing this, you realize that you need some water to clean the cans and the bottles here. You need also water to clean the whole devices here that will that needs to be cleaned to the next brew. Okay, so this is the understanding of what is happening inside the process. Okay, and we define the different steps. From there, we are going to look at what are the real streams. And for defining the hot and cold streams. And for defining the hot and cold streams, we are going to look at inside the process unit operations. Okay, so there we have to realize that there are two types of flows in the system. There are the flows that are the process flows, so the flow of water, the flow of malt, the flow of beer, and the associated or the slave flows, which is the flow of steam that is needed in order to heat the unit. The flow of cooling water that is needed to cool down the flow. So the utilities, and those streams are named the utility streams. So their flows are such that they are supplying the needs to the process in terms of energy. And those are the flows that I would like in reality to minimize. And I know that if I'm minimizing the gas flow, I'm going to minimize the steam flow, and I'm going to minimize the waste, the use of cooling water. Okay? Which means that I have also to realize that I have two different types of systems. On the one hand, there are the streams that are delivering the services, which are the one from the energy conversion system. So, for example, I'm going to have a stream that is going to be to supply the heating. That will be a hot streams that will supply the need to the process, which means that it will be collected to a stream in the process that needs to be cooled down. Okay, so I have to realize that I have this duality between the utility streams that deliver the heat, that are hot streams that deliver the heat, to cold streams in the process streams. Right? So when I have a very complex system, it's not always easy to identify where what are the most important streams to define the heat recovery. And for doing this, it's important to have a systematic approach. And we use an approach which is based on the Pareto principle. And what is the Pareto principle telling us is that you will spend 20% of your time in collecting the information, the 80% of the information. And for the 20 remaining percent, you will spend 80% of your time. Okay? Now, if you want to be pragmatic, just spend the 20% of the time and get the 80% of the information. It's perhaps that the last 20% are not so important or do not have the value of the 80% of the time that you will spend for collecting them. Okay? In order to apply this principle, the way we are going, I would suggest to work is by realizing that the energy that is entering the system is first converted into a distributed form. I'm buying natural gas and I'm going to distribute steam. I'm buying electricity and I'm going to distribute glycolic water. I'm buying water and I'm distributing cooling water in the system. Okay? So if you then look at the way energy is used in the process unit operation, and you identify the vectors that are supplying this energy to the process, then what you can do is to look at who are what we name the energy drivers. So who among the different process units consumes the most of steam? Okay? And typically those are things that are well known by the process engineers. Okay? And let's start to define the 80% of the main users of steam, which defines a list of process unit operations that you have to define. And of course, at the same time, for each of those process units, you will also look at how much electricity they consume, how much cooling water they consume, how much air they consume. Okay? You represent the unit and all the energy consumptions that they need. Okay? And from there, you will be able to define the prioritized unit until you explain 80% of the steam bill. By the way, you have also defined a part of the electricity bill and a part of the air bill. Okay? And then you will start with the second one. So after the steam, I'm going to look at the water consumption. Okay? And again, I will apply the 80-20 rule. So it means that as soon as I have explained at least 80% of the water usage, I'm stopping. But there is a side effect of it, is that I'm defining the main consumers of electricity, the main consumers of steam, the main consumers of water. But of course, I'm defining also them as the user of the other types of energy. And at the end, by applying this 80-20 rule, you are able to define more than the 80% of the energy bill. What we have shown is that we can go up to 95% of the energy bill explained, and by defining only 35% of the units in the system. All the other units are not units that are important from the energy perspective. Okay? So you can forget about them because they do not explain the energy bill and they are not important for the energy efficiency of the system. So it means that from this analysis, I will have a way to target which are the good process units to be considered. Okay? The next step, as I have identified who is important, now I'm going to see what is really needed by all those units that are more or less important. And for doing this, I have to remember the exergy. So you remember the definition of exergy?
That's unavailable work relative to the environment.
With, it's because it is more or less correct. So it's the maximum amount of work that can be produced by reversible processes that do exchange only with the environment. Okay? So this is the definition of exergy. What is the consequence? Is that when I have a stream to be heated, I know that I will have to supply exergy to it. Okay? And the exergy is the value of the work that is needed when I have to heat a stream, or that can be obtained when I have to cool a stream. Okay? From this, I can conclude that the best is when I have to heat a stream, I have to try to heat it with the lowest possible temperature. Okay? The lower the temperature, the less amount of mechanical work I will need. Okay? The same when I have to cool down a stream, I have to try to cool it at the maximum or the highest possible temperature. Right? And by doing this, I will have the possibility of producing a high amount of work. So what I'm going to do is to try to keep this in mind. I will perhaps not explain this, but I will look at every unit and I will try to understand where they need heat and where they need cooling. And as soon as I know something that needs to be cooled down, I will have to try to cool it at the maximum, the highest temperature possible. And when I need to heat up something, I will try to keep the temperature the lowest as possible. Which also means that I will identify the streams that needs to be heated and the streams that needs to be cooled down. Where do I find the streams that needs to be heated and the streams that needs to be cooled down? Mainly in two different types. So they are the ones that are in heat exchangers, already doing heat recovery, okay, for which I will have to characterize both sides. And then all the ones that are related to the utility. And typically there are a lot of streams that are heated by or cooled down by utility. So it's the streams that are using the heat exchangers that are using steam, for example, or hot water, and the heat exchangers that are using cooling water, right? Okay, so those ones are the ones that I typically have access to because they are related to a flow that I'm paying. Okay, the flow of steam, the flow of cooling water, right? So what I'm going to do now is to look at the requirements by saying, okay, the process needs to be heated and the operation is happening at a given temperature inside the process. Perhaps that this process needs hot water, is using hot water, sorry. So it means that now I can decide that the process that needs to be heated will be heated by supplying the hot water instead of heating the process directly. Okay? But then I can also realize that perhaps this hot water is produced by steam. So now I can decide that instead of considering that I have to heat hot water, in fact I have to heat to produce steam. Okay? By doing this, what is going to happen is that the temperature level at which I have to supply the heat is going to change. Always the same amount that I can measure from the flow that is in my the flow of steam, for example, okay? But the temperature level is going to change. If I have to produce the steam, I will be at this temperature level. If I have to produce the hot water, I will be here. If I have to heat the process, then I will be here, okay? And what you can see is that the closer I am from the process, the lower is the exergy required to heat the stream. The same amount of heat, but with different quality. Something which is here important is that we define those three types of interfaces. So the black box that is mainly producing with a boiler or a cogeneration unit the steam that is needed by the process. The gray box representation where we say, okay, we are going to look at the temperature at which the steam is used, so for which purpose the steam is used. And the third one, which is the white box, is when I'm able to represent what is happening inside the process unit. Typically there, I will need models, okay, because I will have to look at in the details. And I will give you one example of this approach by looking at this process unit. So this is a process unit, and a priori, this is what I see. A flow of steam, a flow of cooling water, a flow of electricity, a flow of raw material, and what I can tell you is that it's a separation unit because it is separating two flows here. So if I have to represent this amount, the first thing that I can do is to say, okay, let's produce the cooling, the steam that is needed. So I have, therefore, a cold streams that takes the condensate here and needs to produce the steam. So I have a cold stream like this one, okay? Preheating the water that is coming back and then evaporating to send the steam back at this state here. And the same for the cooling water. So here, the cooling water has been heated in the process unit, which means that I have to send it back to a cold state. So it means that I need to cool down this stream, hot here, to a lower temperature here. Now, if I'm looking at what is happening inside the system, I realize that the separation is done by a distillation column. A distillation column needs, in fact, has a boiler in which the steam is condensed to supply heat to evaporate the mixture here. And the distillation column has as well a condenser in which the vapor that has been, of the fluid that has been separated, is condensed and is heating the cooling water. But what is happening is that this temperature is higher than the temperature of the cooling water, and this temperature is lower than the steam that is condensing. Which means that I can then replace this hot stream, this one, by this one, which is at a lower temperature. And the same, the hot stream that was in the utility system can be replaced by this one, which is what is happening here, which is the condensation of the boiler. If now I want to do the same operation but going into the details, then I can even go inside the system. So I realize that the distillation column could be, the flow could be preheated first, and that the heat transfer can be not only done by the condensation here, by the evaporation here, but can be then distributed or spread over the whole column, which gives a profile like this one here, with streams to be heated and streams to be cooled down. And what you can see is that the temperature level is lower for the streams that needs to be heated and higher for the streams that needs to be cooled down. And of course, I still have the opportunity of creating another unit that would do the same separation on a different way. Okay, so from there, I have defined different ways of analyzing the process unit operations. And I'm going to give you some examples just before the break. And the first one is, how do I represent a mixer? This is something that I have already shown once. When you have a mixer, so a mixing is a process unit operation. Okay? And so what you can see is that if you think about what is the heat needs of a mixer, then you realize that, in fact, this stream that is at 80 needs to go to 31, while this stream that is at 15 needs to go to 31. So at the end, I have a hot stream and a cold stream that needs to be considered as hot and cold streams. And from there, I will be able then to identify the possible heat recovery. So now if at the level of the system the pinch is at 45 degrees C, it means that this stream needs to be cooled down from this temperature to 45 by doing heat recovery above the pinch, which means that only the part from 45 to 31 can be done directly in the mixer here. But which means also that because I had this 140 kilowatt that were available in the stream that is now recovered, meaning that I need to find a hot stream to supply the heat that is needed to compensate the 140 that are not anymore available here. And this will be done by streams that are available from below the pinch. And I know that I have enough, because I have identified the pinch. Okay? Which means that now I will have to preheat this one for 15 to 26 before doing the mixing at 45 before making the mixing between the 45 and the 26 to reach the 31, which was the target temperature. Okay, so I'm going to stop here, make a short break, and then after the break I'm going to show you examples on how to identify the hot and cold streams in the brewing process. Okay? I'm going to explain a little bit the way to define the different streams that are in the process by, in fact, taking the same process as the one that I have been explaining, where you can see that you have the mat preparation, the mash preparation here, then a preheating here, a cooking, a filtering here, and then a cooking here, followed by a cooling that will then go to the fermentation section. So the idea here is to try to identify what are the streams that needs to be heated and the streams that needs to be cooled down. And something that we can realize here is that as the water is used everywhere in the process, they have decided to produce hot water here. So they produce hot water that is maintained at a certain temperature, and that is then afterwards distributed here and here, and then the complement is done by water injection or vapor condensation. Something which is also interesting to mention is that this tank that is used here is preheated. So it means that they recover the heat from the hot beer that is here, of the wort here, to preheat here the water that will be used as well. And the question is, how do we define the hot and cold streams in the system? So first, let's look at this operation here. So it's the MAC where we have three streams that are mixed and with the hot water at 80 degrees C that is heated here. So this is the extract of the system, and what I can realize is that in fact if I want to define what is needed, well, I realize that I need in fact hot water, so it means that I will have to produce this hot water. So let's look at how it works and how we can make this operation. And of course, so what I can decide is that I have to produce this hot water at 80 degrees C, which, because it corresponds to the needs here, so it means that I will reach the 48 here by producing hot water from ambient conditions, because it's a process stream, to and heating it to 80 degrees C. I can have another option. The other option would be to say, okay, let's mix the streams at 15 degrees C and let's make a heat exchange with this mix that is in the tank here at, and that has to reach 48 degrees C. So it means that what my system will see as a temperature requirement is something which needs to be heated at 48 degrees C. But I can also decide that instead of doing this, I would preheat this one, preheat this one, preheat this one, reach the 40 degrees C by introducing 3 cold streams that would reach the 48 degrees C that is needed. So now what you can see is that I have 3 different definitions of the same requirement. Either I'm producing hot water, or I'm heating everything in the tank, or I'm preheating all the flows. And of course, something which is important here is that the mass balance still remains the same. It means that the fresh water that needs to be heated at 48 degrees C is in fact the fresh water plus the hot water that was injected in the past, so that I keep the unit operation working the way it was working in the past. Okay? So 3 different types of heat, of cold streams representation for the same amount of heat to be supplied. And of course, the one that is the most attractive from the exergy point of view is this one, so the red one. Okay? This is the one that requires the lowest amount of exergy. Okay? So my message here is that you have to analyze process units, and this is a very simple one, it's just a mix. But you can see that a mixer can be represented in very different ways when you have to do to realize the process unit operation. And something which is important here, for example, this one, which is the most attractive one, is perhaps not the best one, because it's not so easy to heat malt and heat corn in a heat exchanger. So perhaps I will have to use part of the water that is here to mix with the malt and the corn in such a way that the whole mixture will reach 48 degrees C. Okay? Another example is what is happening at the in the evaporation section here. So if I'm looking at what is happening there, what I can see is that I have a stream that is heated, that goes into this unit, and that is separating the gas from the liquid. So it means that in reality what I need is to preheat the flow that is entering the evaporator to reach the temperature of evaporation. I will need to supply the heat for doing the evaporation at the temperature of the evaporation. And I will need to cool down, I'll have the opportunity of cooling down the gas that is today vented, but that can be cooled down at the pressure and the temperature it is produced, and go back to what? Environment. So it means that I have to cool it down to 25 degrees C. Okay? So it means that now I will have, on the one hand, this part which will be represented by this preheating slope here. What is happening here, which is the evaporation, which is happening, going, this part here is from there to there, and then going here for the evaporation. And on the other hand, I will have this stream, which corresponds to the condensation of the steam that is here, and then the cooling down of this one to the ambient conditions. So it means that I have defined now the requirements, not only by a heat to be supplied to a system that is going to make the evaporation, but a list of steps: preheating, evaporation, condensation for heat recovery, and then cooling down. And by doing this, I have defined the streams in a rational way. Okay, do you have questions about this? Typically there are no questions, so you will have to then, as you do not have any questions, you will have to find what are the hot and cold streams of the cleaning system of the bottling process. And the cleaning system is the following: is that you have dirty bottles that are entering here, Those bottles need to be rinsed, so they will enter in a machine that is going to spray water at 60 degrees C in order to clean the bottles, so don't rinse the bottle. Afterwards, the bottles will will receive some soda water. So it means it's high temperature water that is mixed with soda to clean the bottle here. So this hot water is sprayed on the bottle to clean the bottles, and then the hot bottles will come here and will go to the final rinsing, which will use the 15 degrees C here to rinse the bottles so that the bottles are clean and cold when they leave the process. Okay? And what we can see for doing this, we need hot water for doing the pre-rinsing, we need at 60 degrees C, we need hot water at 85 to clean the bottles, and we need water at 15 degrees C to cool down the bottles here. Okay? And the question, and today we are using steam here for producing the 85 degrees C, and here for producing the 60 degrees C. Something which is important as well is that you can see that there is, in fact, the water that is injected here to clean the bottle is recuperated. So the temperature is lower because I have to heat the bottles. Huh? Yes?
The idea of getting some of the soda down to the recovery just to increase the temperature, right?
The idea is to recover water. Okay, so you can see that the water that is coming here is going to be dirty because it's mixed with the clean water and the dirty water here. So diluted here. And then what we do is that there is a recovery here so that we minimize the amount of water that goes to the wastewater treatment plant. And therefore, the amount of water that I have to put in the system. Okay? So it's a trick in order to avoid having too much spending of water. Okay? So now the question is, looking at this flow sheet, what are the hot and the cold streams? So you have 15 minutes. So what I propose is that I'm going to show you how I've done the analysis, and then I will let you compare with the one that you have generated. Okay. And this is the solution that I would propose. So what is important is that we have to realize that there are, in fact, three process operations. The first one, which is the pre-rinse here, the second one that is the washing that is done here, and the third one that is the final rinse. So this is the need of the process. Okay? And the needs are expressed as the amount of water that needs to be flown against the bottles here, another amount of water at 85 degrees C that needs to be used for the washing step, with an additional constraint that is here, that is saying that the quality of the water there has to be maintained, that what is justifying the fact that we just not loop the water, but we have to add soda and we have to add raw water. That's mainly because otherwise you will concentrate the dirt in the water, okay? And then afterwards, once you have washed the bottles needs to be are going to be cooled down. There is apparently no specification here, so it means that we can do what we want there. But again, so the system needs a certain flow here, and this flow is in fact made by recycling. Okay? So at the end, if I'm looking at what is needed by the process, what is needed by the process is a certain amount of water that has to enter here, that needs to reach the 85 degrees C, so that we will have a given flow here, which is a mix of the water and the soda. Okay? And I've deduced this flow from this analysis here, because I know how much water needs to be looped here. Okay? Now, this water is going to exchange heat and, in fact, take also dirt here is exchanging heat with the bottles, and therefore it is going to decrease the temperature of the bottle of the water from 85 to 65. And you need to recycle it, so it means that you need to reheat it from 65 to 85 in this loop. So it means that at the end, I need 1, 2, and 3 heat exchangers with 3 cold streams. Now, due to the constraints of the amount of water that needs to be used in order not to accumulate dirt, okay, I have a certain amount of water here that is leaving the system at 65 degrees C that I need to cool down. So I take the part of the water that is here and I'm going to take it to cool it down to reach the 60, which is the demand of the pre-rinse operation. The pre-rinse operation is asking me to a certain amount of flow at 60 degrees C. And I'm going to do it to satisfy this demand by, on the one hand, preheating the cooling water that is entering here, which is also raw water, okay? That is going to be used in order to do the final rinse. I have a recycling here, just because I want the water to be clean. And then the water that is living here at 35 degrees C, after having cooled down the bottles, will be heated to 60 degrees C, okay? Because they need to reach the 60 degrees C here. So the one here is going from 65 to 60, this one is going to 35 to 60, and the water that is at 40 after the pre-rinse, okay, that has been cooled down in the pre-rinse, will be heated back to 60 so that I have the temperature that is needed for doing the pre-rinse. And then there is an additional option which is appearing here, is that the water that has entered the system has to leave the system, okay? And it's leaving the system in form of dirty water that is going to be go to the wastewater treatment. And I can use the heat that is available there for the heat recovery as well, meaning that I'm going to define a new hot streams that goes from 40 to 20 degrees C. Okay? So what you can see here is that there is no need of steam anymore. Okay? Everything that needs to enter the system has been heated at the temperature where it is needed. So the water, the soda, is preheated to 85 degrees C. It is going to be cooled down here, delivering the heat, and then being reheated here. And then I have an isothermal mixing here, and I'm recovering the heat that goes to the environment. Okay? By doing this, I think that I have made the correct definition of the hot and cold streams in this cleaning system. Okay? So, and this gives me the conclusions of this part of the course. So how do we define hot and cold streams? The answer is look at the process. So forget about the utility first. Look at all the process streams, the process energy needs, which means analyze the process units. Try to not forget exergy, so it means that as soon as you need heat, try to do it at the lowest possible temperature, and when you have heat, try to do it at the highest possible temperature. Avoid non-isothermal mixing. When you have an injection, go back to the state of the stream that is injected. So for example, here the goal was, if I have to produce steam, then I realized that the steam is part of the process, meaning that the steam has to enter from outside, be preheated, and reach the steam temperature. So evaporated and reach the steam temperature. That means that it would be a cold stream from 20 or 15 degrees C to the saturation state plus the vaporization at the pressure at which it is injected here. And of course, something that you have also to be sure is that the streams that are entering the system or that are leaving the system have to be the closest possible to the environment. Okay? So never consider that something is entering at 80 degrees C, okay, without having a very good justification. Otherwise, someone else has paid for this heat, and you will be charged. Okay? So the streams that are leaving the systems needs to find a state or reach a state that is in equilibrium or as close as possible to the environmental conditions, which is again a result of the exergy analysis. Okay?